I'm going to talk about a new application to computer science of high-dimensional expanders. And this is joint work with Farad Harsha, Tali Kaufman, Inbal Livni, and Amnon Tashma. So yeah, last week I gave like 4 hours on stuff, so I exhausted all my slides that I had. So now I was forced to create new slides. So I hope it will work. Okay, so I'm going to start by talking about the high-dimensional expanders, the definition that I want to pursue here. So first we start with a simplicial complex. It's just a hypergraph that's downwards closed. There will be no topology in this talk, so X will be the complex, and then you have XD will be all the D faces, X0 will be the vertices, and in between you have faces of increasing sizes. Now, when we start with a simplicial complex, we can think of a distribution that is uniform over the D faces. And then, if you want to know what is the distribution over D minus 1 faces, you choose a random D face and you remove a point from it. You get a distribution over D minus 1 faces that doesn't have to be uniform, because there might be some D minus 1 faces have more D faces containing them and some have less. So they will get different probabilities. And for the constructions that we care about, this actually happens, so we must talk about these distributions. It would be really great to get a construction that is regular, and then I don't have to worry about the distributions. But for now, I have to worry. So these are the distributions. Pi I is obtained from pi d by choosing a random D face and erasing D minus I random points. And all of these pi i's live together. It's a joint distribution. And this is like the correct distribution from my point of view to talk about the complex. Just like if you have a graph that's deregular, you never think of the distribution over the vertices. It's uniform. But if it's not deregular, then vertices that have more neighbors have more weight. So this is the analogy. Right. So a priori, if you think of like the quotients of Brutitz buildings and stuff we've seen, the top distribution will be uniform. But later we will look at complexes that used to be these complexes, but then we forgot about all the top dimensions. So we start with some dimension, and we already have some distribution on it. So I want to talk generically, so I have distributions across the board. Okay, so as I said before, really, if this is confusing to you, then think of everything uniform. But I must warn that we don't know of any construction that is uniform. So, okay.
Regular means, in a very strong sense, that any two faces of any dimension can be mapped to one another by an automorphism?
No, much weaker, just like regular in a graph, that every face has the same number of top faces containing it. That's what I mean by regular. But we don't have such constructions, as far as I know. Okay, so now I want to give the spectral definition of high-dimensional expander. And gamma will be like some small positive number that to me is like controlling the error. Okay, so what is it? So first of all, what is a gamma expander? Okay, so a gamma expander, you have vertices, this is x0, and you have edges, this is x1. And what does it mean for it to be gamma expander? Well, look at the adjacency matrix of this graph, normalize it, so that all the eigenvalues are between -1 and 1. And then you want that all the non-trivial ones are between minus gamma and gamma. Okay, they're very small. What about for a higher dimension? So we want this to be the case for the x0 and x1. And also, there is a local link condition. And the local link condition says for every face S in xi, for any I less than d minus 1, the link of S is something interesting. So this is the one skeleton of the link of S. And for people who don't know what this is, I'll define it now. So you want that the one skeleton is this gamma expander. All the non-trivial eigenvalues are between minus gamma and gamma. So what is this XS? Let me just do the whole thing. So let's look at the picture instead of the definition. So you have a face S. Okay, its dimension is I, so it has I plus 1 points. And now look at all the neighbors of this face. What are all the neighbors? It's points such that there is a face containing all of S and also these points. This is the definition of neighbors of S. Okay, so all these points are XS0. These are the vertices in this graph I'm defining. And now there's also edges in this graph. What are edges? These are pairs of points that there is a face containing S and this pair together. Okay, so these are the edges in this graph. Okay, so for every S we have this graph. It's related to the link of S. And you want that this graph is an expander as well. It should be a gamma expander, just like before.
Consider -1 trivial?
Thank you. No. So in the high-dimensional expanders that we get from quotients of the building, the links, like this graph, will be partite. It can be bipartite. It can be even, there can be more parts. For example, if it's bipartite, there's going to be a -1 eigenvalue. So it doesn't satisfy this definition. Okay. But this is the definition that is the most convenient for me. So let's talk about whether it exists. Okay? Okay, so for D equals 1, it exists. Expander graph satisfies this definition. For D bigger than 1, it also exists. The complete complex. So what is the complete complex? You have n points as the vertices, and then you have n choose D for any D face, say up to D. Okay, so you look at all possible faces that you can put on n vertices. What does the link look like of the complete complex? So think of a face S. All the points that are vertices not in S are neighbors of this S. And all the pairs between them are edges in this link. So the X sub S, in this case, is a complete graph for every S. So in particular, it satisfies that it's a gamma HDX. Is this clear? Okay. But it's not bounded degree, which is what we will care about. Okay, so for graphs, we know that what we do is we can look at a random construction where you just choose every face with some probability. This never works. There's no value of P for which, if you choose the triangles with probability P, you will get such a thing. It doesn't never work. Of course, Lineal and Mishulam showed that it does work, but not in the sparse case. So if you try to set up your probability so you get a sparse thing, you will never get an expander. And it's really kind of amazing that it does exist, but we know it exists. So if you look at these high-dimensional expanders that we have, they satisfy this definition except for this problem that Costa was mentioning. It's a one-sided version. So the eigenvalues are not between gamma and minus gamma. They're just below gamma, but they can be all the way to -1. Okay.
Let's be fair. If you take this as your definition, then this fact is already in the work of Garland. It's not in our work. I mean, we made use of it to other properties, but this was Garland.
Garland constructed finite things? I didn't know that.
Garland, basically, the method that he proved that the cohomology vanished for this quotient was exactly by saying that all the links are extremely good expanders.
No, I didn't know he talked about quotients. I thought he talked just about the infinite object.
No.
I thought you guys were the ones talking about quotients, so I apologize. So let's be fair. Okay. Sorry, okay. Fair enough.
We made the use of it to other problems, but this was really his point. He didn't use the language of expanders.
Awesome, okay. All right.
That's exactly what the crucial.
Okay, so thanks. Okay, so I have some papers I will need to fix. All right, so nevertheless, I want to talk about this definition. So we have a lemma that says that actually there's an infinite family of graphs that have this two-sided HDX thing. So can anyone, okay, never mind that. The way to do this, it's like a trick, yes? you start with an expander that's a quotient of the building, so you know exactly what the links look like. Now, if you have a link of every face in the building, it looks it's partite, as I said. Okay, so if you're in a d-dimensional building and you have a face of dimension I, then the link looks like d minus I partite. Okay? And if I is small enough, d minus I is very large, then this graph, the eigenvalues are actually small. Okay, this is a claim I'm making. So if it's two-partite, the smallest eigenvalue is -1. If it's three-partite, it's already some minus, I don't know, 1/3, 2/3, something like that. And if it's a million-partite, then the eigenvalues are something like 1/1,000,000. Okay, this is what I'm claiming.
In absolute value, I'm a little confused what you mean, or just
Yes, minus. They're at least minus 1/1,000,000.
what's this? I don't understand. What does it mean? That the number of d-faces is bounded by constant
Times the number of zero faces. So this is like your theorem, or maybe you say Garland. Okay, Garland's theorem. Except that I'm saying it's with my two-sided definition. So I'm saying that the eigenvalues can be bounded on both sides, not just on one side. And what is the proof? The proof is take a d-dimensional complex like Garland, and then look at a skeleton of it of dimension k, where k is much smaller, like gamma times d or something like that. And then you will get that down there, all the links are million partite, so they actually have good.
Say for every d, these three.
Because for every d, I first take d to be 1,000,000, and then I take the 3 skeleton of that. So it's for every d. For every d and every gamma, you have this. What do you lose? The only thing you lose is that the top distribution now, since you're looking at a skeleton of something else, it's not uniform anymore. That's why I bothered you with the distributions. Okay. Anyway, so for the rest of the talk, we don't need this. All we need to know is that these things exist in bounded degree. Okay, so now what I want to talk about is that the high-dimensional expanders can be viewed as some kind of sparse model for the dense situation, so for the complete complex. Okay, so here are so I want to discuss this a little bit. So bounded degree expander graph, you can view it as a sparse model for the complete graph, right? For example, in the expander mixing lemma, you show that the fraction of edges between S and T is the same as in the complete graph. Okay, so now I want to say that the analogous thing holds for the dimension D. So a gamma high-dimensional expander is a sparse model for, let me denote it by K and D. I don't know the standard notation for this, but this is the complete D-dimensional complex. So, it's like a pseudo-random object. Like we think often of expander graphs as a pseudo-random object. So here, I cannot use the term pseudo-random because you cannot construct these things randomly. But so instead, let's say it's a pseudo-dense object. Okay, it behaves like the dense object, but it's sparse. It's more efficient. Okay. Okay. So, in what ways am I making this kind of blanket claim? So why am I saying it? So one thing is, if you look at the high-dimensional expander and you start to count, you mark some set of vertices and another set of edges, and so on, and you start to count faces between them, you get the correct number in the sense that the number is like you do in the complete complex. So it's like an expander mixing lemma. And this was shown by Evra, Golubev, and Lubotsky. However, this actually holds also for much weaker definitions of things, like paths in an expander graph also satisfy something like this. So it doesn't yet capture kind of the strength of what's going on here. Another thing is that you can look at random walks on every dimension. So something like this. So okay, ignore this stuff. So it's like you start from an I face, you go to a random I+1 face that contains it, and then back to a random I face inside of it. So this is the upper Laplacian. And you have these kinds of random walks for every I. And you can ask yourself, what is the spectral gap of this random walk? Turns out that in these graphs, the spectral gap is exactly like in the complete complex, up to an error that's controlled by gamma. And this actually is already quite powerful. For example, with Tali, we proved that it implies something called agreement expansion. This is a kind of a PCP question, which I'm not talking about today, just to say that earlier works proved agreement expansion for the complete complex, and in this work we showed that because of this property, you can prove it also for the sparse model. And in another very recent work with the... Yes, we published it this morning. With Yuval, Filmus, and Prahlad Harsha, we showed that you can actually analyze functions, so Boolean functions or real-valued functions on XD in a very similar way to the way you analyze them on the complete complex. Then it's sometimes called the slice. So just like you have, analysis of Boolean functions on the 0, 1 to the n, you can do it on 0, 1 to the n when you only look at strings that have exactly d plus 1 ones. That has size n choose d plus 1. And it turns out that you can do the same kind of thing even on x to the xd, which has only linear in n number of points. So, okay. Yeah, so when you prepare a talk, so it's something I learned is they say, cut your darlings. So I prepared a whole couple of slides on this, and then I cut it out. So
the audience gets to resurrect.
at the end of the talk, you can, if you're still awake, you can ask me again, okay? Yeah.
I remember the time that Spielmann has his theory of
Sparsifiers.
and then Ramanujan graphs were exactly sparsification of the complete graph.
Yeah.
It was something which was quantitative. Do you have such a quantitative notion for I-dimensional?
So all these are quantitative, but they're different questions, right?
Is
So
it possible that the Ramanujan complexes, that was kind of my dream, Ramanujan complexes will be the sparsification of the complete
yeah, I think I also believe in this dream, but give me a, you need to come up with some kind of question for which then this is the answer, right?
No, so
The answer is positive. We did it with Ilan.
What?
With Ilan in 211, it published in Soda. The theory of Spielmann applies to higher dimensionals in this sense. How it's for every coboundary, the density will be as you want, and you don't even have to take complete graph. You can take any d-dimensional complex, and you take it. The Spielmann method applies. It works. How does it?
Okay, yeah, I also want to hear about that. Okay.
There's not one, you can't say one sentence up for?
Yeah, I can say, fine. You win. Okay, so look, on the slice, you take any function from, from n choose d to the reals, and you can write it as f equals summation fi for I from 0 to d, right? Like the constant part, and then the degree 1 part, and the degree 2 part. So you can split any function into a sum of homogeneous parts. They are orthogonal to each other. And you can also analyze like the natural random walk on the slice, where you take a string with d1s, you erase some one, and you add another one. That will be like your noise operator. And you can analyze all these homogeneous parts have the same eigenvalue with respect to this noise operator. Right? And then we look at the noise and we do nice things. So here, the same thing holds. You can write any function on xd as a summation of fi, for fi will be like the homogeneous part. They won't be orthogonal anymore. They'll be almost orthogonal, and the distance from orthogonality is governed by this gamma parameter. So they're almost orthogonal decomposition. And they're almost eigenvectors. So they have the same eigenvalue like on the complete complex up to this error of gamma. So everything is true, except you always have to add this gamma error everywhere.
So it is like an almost spectral structure that looks similar to the one on
To the complete complex, yes. And we also prove an FKN theorem. So there's just like some theorem on the slice that talks about the structure of Boolean functions that have degree 1 or are close to have degree 1. And we prove a similar theorem here. You can analyze the structure using this decomposition. Just, you can view it as demonstration that this is useful for something. I don't know. Okay. But now, today, I will talk about a new application of these pseudo-dense objects to list decoding. So I want to tell you about double samplers and error correcting codes, and then do this. So who is my chair? So what time are we going until?
Started on time.
12:20. Okay, fine. So my goal, first I will define double samplers. Okay, then we will talk about some application to error correcting codes. So let's start with double samplers. So first, even before that, let's define samplers, which are common objects in TCS, theoretical computer science. Okay, so what's a sampler? You have a bipartite graph, V0, V1, and you say that it's an alpha beta sampler if for any function here on the vertices, or even think of just a subset, if you want to know what is the measure of this subset, it's almost captured by looking at a typical vertex here and asking how many neighbors does this guy have in this subset. So to be a bit more formal, you say for every function, now the function is no longer, doesn't have to be discrete. It can be in this segment between 0 and 1 for every vertex. And you define a number, f sub s, to be the expectation over all the neighbors of s of fu. You see, so s looks down at all of its neighbors, and it averages their value, and it gets some kind of number. And this number should be very close to the global average. Okay, so then you say that this graph is a sampler. Okay, so the sampler just means that the local S average is the same as the global average.
And from V1, we sample uniform.
Yeah, you know what? From now on, we forget about all this weight stuff and just think of regular bipartite graphs and so on. Okay, so just to tell you, it will be most convenient not only to think of it as a bipartite graph, but also to think of this as a family of subsets of V0. Every S can be identified with a subset of its neighbors. So you can think of a sampler, you have n vertices, and then you have a family of subsets of those n vertices, and it's going to be D regular, so every subset here will have exactly size D. Okay. Okay, now moving to double sampler. So now we just add one more layer, V2, on top. And we want that everything that you see is a sampler, so let's see. So now you have a 3-layered graph, V0, V1, V2. And let's first look at this requirement. So you want that this bipartite graph is a sampler. You also want that this bipartite graph is a sampler. And you also want that the bipartite graph between V0 and V2 is also a sampler. And you can imagine what that means. It means that you follow length 2 edges. Okay.
So, but V0, V2 is already, I suppose, a multigraph.
Yeah, let's add the weights of the edges. Yeah.
You count how many paths.
You count how many paths. Yeah. So actually, so far to get this, you can just take 2 bipartite expanders, and you will get something that satisfies this property. But here comes the double in the double sampler. So this is a property it's not easy to get. For every t in V2, so now again, remember, I'm going to think of every vertex as a subset. So also every t up here, you can view it as a subset of all of its vertices. Okay? So look at all the neighbors of t in V1 and at all the neighbors of t at V0. Call them V0t and V1t. Okay, so this induces a bipartite graph here, right? Just on the neighbors. I want that this bipartite graph is also a sampler. For every t. Now think if we try to construct such a thing by taking some expander graph here and some expander graph here, it is very likely that these guys don't have any common neighbor. Okay, so the bipartite graph induced by looking just at the neighbors of T will look like a bunch of stars. It will be very, very far from being a sampler. A sampler, you should think of it intuitively as something that's like an expander. So if you have a disconnected graph that has just stars like this, it's a very bad sampler because I'm going to take my function to be 1 and half the stars. All these neighbors are going to think that the expectation is 1. All these neighbors are going to think that the expectation is 0. And no one will know that the right expectation is 1/2. So I hope, is that kind of clear? Okay, so anyway, so this is non-trivial. I'm claiming, okay, it's not completely non-trivial. If you take the complete complex, you will get this. But we want it to be constant degree.
But what the example that we just discussed, we took a random graph for both random and regular graph, that would be a double sample, right?
No, why not?
Same thing.
You will see for a specific T, look at just at the bipartite graph induced by the neighbors of T. So it will be a bunch of stars that are disjoint.
No, but if the degrees of the stars are big enough, it would be a sampler. So
No, never. They will be disjoint stars.
One, you say. I mean, you get a half.
so for example, if the probability is 1, you get the complete. So if the degree of every star was
No. If it's a star, it's bad. If the degree is very high, you won't get disjoint stars anymore. If the degree is huge.
Why random is not?
Yeah, I can read. In a random constant degree graph, the local, what you see locally from T, you look at all the neighbors of T. These are subsets of T, and they further have subsets of vertices. And in a if you choose these things randomly, this is how the graph will look like. There will be no common neighbors. And so forget about this. This is your graph. It's disconnected. So it's not a good sampler. Okay? If you start choosing many, many, many edges with a density that's almost full, you will never have disjoint stars and you will be in good shape. But if the density is small, like a bounded degree, this will never work. If you add edges where? You know what? Let's talk about it after.
Why this is bad that it's not connected?
Why is this not a good sampler? So let's draw 4 just so I have a good. So here is a set. Forget about these extra edges that I added. Imagine they are disjoint. So here is a set of vertices. I assign 1 here and 0 on the rest. The expectation is 1/2. But this guy thinks that the expectation is 1, and these guys think that the expectation is 0. So no one thinks the correct thing about the expectation. In a sampler, you should be the same. Okay, but just to get intuition that such a thing exists, if you take n vertices at the bottom and choose r vertices at this level, all possible n choose r, and all possible n choose r squared up here, then actually you get a double sampler. Because look, what does the neighborhood of some specific guy here? So some specific guy here is a set of size r squared. All of the r squared choose r subsets are present. So here you have r squared choose r, and here you have r squared. And this is the complete kind of bipartite graph. Not complete. It's like whatever it is, it's fine. The edges are for inclusion. The edges are, when I think of set systems, it's always inclusion. Okay. Okay, so we said it's easy to satisfy one requirement, but not both. Okay. So I said already that gluing 2 samplers, like one on top of the other, will not be good. As far as I know, I don't know how to do it. And kind of one interesting feature that you have here is that in a double sampler, the bottom layer, for every T, what you see is itself a sampler. So it's all globally a sampler, and also kind of there's many local pieces that are samplers, and they're all kind of spread around uniformly. Okay, maybe we'll see it when we see how we use it. So how do you construct such a thing? So two constructions are easy. One is the complete, like I said, with the R squared and R. Another, you can take kind of the Q analog. So you look at your vertices as you identify them with points of a vector space, and then you take, some d-dimensional subspace and some other d-prime dimensional subspaces, and you connect. You will also get a good double sampler. But these are not sparse. They're not bounded degree.
This doesn't have a problem that you take n-dimensional subspace and this doesn't break in the same fashion?
I don't think so.
Included in
No, I don't think so. Yeah. Okay, but I admit I kind of added it late last night, so.
I don't understand the definition of the graph sampler.
The points are going to be your points in a vector space, and then you take the lines and the planes. So every line looks at q points, and every plane looks at so many lines and looks at q squared points. Okay. So now what are we going to do? We're going to take this. Instead of n choose r squared, we're going to take the r squared level in the expander, and then v1 will be the r dimensions, and v0 will be just the vertices. Okay. And this will also have, this is easy to prove that it's a double sampler.
By the way, is R squared and R just an example of D and D prime?
Yes, yes. Nothing is special. No, thanks, yeah. Okay. Okay, so this works, so we took it and fine, but it's kind of very intriguing to ask what can you hope for? What is the best double sampler you can get? For example, okay, we got sparse, so we got that the number of sets in V1 and V2 is linear in n, but how small can it be, right? So if I fix gamma, or I fix the parameters of the sampler, what is the smallest size of V1 and V2 that I can get? So, all right, so this is open. And just to say to the people, Ramanujan is kind of best in terms of imitating the spectrum of the tree. But here is another thing you can try to optimize, and there's no reason to believe that when you optimize the spectrum, you also optimize this.
And in the comment, we still don't know what the largest Chigel constant is of
The largest.
Tato, I should repeat this often because somehow people think the problem is
But you have your chance this afternoon.
oh, less politely, shut up.
לא עבד לי. Okay.
Sorry, but to optimize this meant to optimize what? Instead of spectrum, you want to optimize?
I want to say what is the degree of your sampler and what is the alpha beta of my sampler, and that's it. And now you need to tell me what is some upper bound that or lower bound actually that I need at least this number of vertices in V1 and V2. Usually in the whole theory of pseudo-randomness, we always have the random construction as our yardstick. We can always say, if you try to construct an extractor, the random extractor achieves these parameters, we should try to imitate it. But here, I don't know of a random construction, so I don't have a good yardstick. So this is the question here. Okay, so we define double samplers. Now we move to error correcting code, and I want to show an application to list decoding. Okay, so this is stuff we all know. So a code is a subset of n-bit strings, and the distance is for any distinct points in the code, at least delta fraction of the coordinates are different. So I say the distance is delta. And we're interested in codes that you can actually decode in polynomial time. So a decoding algorithm gets some word W, doesn't have to be in the code, and it needs to find some word in the code that has distance from W that's smaller than delta over 2. Because of this distance guarantee, there's only a unique answer, and this is what the algorithm should do. Or, of course, if there is none, it should say there is none. So this is a decoding algorithm, and now there's also a list decoding. So if you only want to find things in radius delta over 2, there's going to be a unique answer. But there's also a notion of list decoding where you allow yourself to go all the way up to distance delta. And then there might be more than one W, but there aren't many. We know this by the Johnson bound. So a list decoding algorithm needs to give all of these. So it's the same thing. You get W, you need to find every Wi that's within distance delta of your W. Sorry. Okay, so this is standard. So here's a well-known and well-loved distance amplification transformation for codes. This is due to Alon, Brook, Nor, and Roth. So here it is. Maybe you've seen it. So you have a sampler, just a normal sampler, and you have a code on n bits. So here you have n bits. And you put the code word here in the bottom. Maybe I have it. So you put the bits of the code word here in the bottom, and then every vertex just aggregates the bits that it sees. And so this guy is going to see a string of length 3, 0, 1, 0. Okay, so here it is. And the second guy aggregates its neighbors, and it sees some other small string. And every guy in V1 aggregates just the local view that it sees. Remember, if we think of this as a subset, then in this subset you write the local view, the value on these elements in the subset. Okay, and you look at the list of everything, and you call it a new code word. So now this is a new code word in C prime. It's no longer binary, so every symbol is a bit bigger. And also the length of it is V1. Okay, so call it F sub W. You can think of it as a string. The indices of the string are V1, and every element is from a bigger alphabet. So here it's 0, 1 to the D, if D is the number of neighbors you have. Okay, and look at C prime. So the claim is, it's very easy to prove, is that if W had even very small distance, some constant, sorry, not W, C. If the strings here were always guaranteed to be at least delta apart, then look at some code word. It has at least delta fraction 1s. How many guys on top will see this fraction? Because it's a sampler, many of them will see it. Actually, it will be very small probability to not see this part. So almost all of the symbols here will be non-zero. So you get a huge distance amplification this way. And here it says that if the distance of C is alpha, and this guy is an alpha-beta sampler, then the distance of C prime is 1 minus beta. So we think of alpha and beta as very small. We got from distance almost 0 to distance almost 1. And what did we lose? Earlier the block length was n, and now the block length is the size of V1, so it's still O of n. And also we're over a non-binary alphabet. Okay. So this is kind of used many, many places in various constructions, this transformation. Let me tell you how we decode this new code. So suppose for the original code C, we had an algorithm. How do you get now an algorithm for decoding C prime? So it's very easy, by majority. So what does it mean, an algorithm for decoding C prime? You get some word up here, and this word is not perfect, right? It actually has many places that are erroneous. And your goal is to find a close by code word. So you need to, basically what you do is for every vertex here, you look at all of its neighbors, and you see this local view thinks that I am 0. This local view thinks that I am 0, and this local, okay, here I have 2 neighbors. This guy has 3 neighbors. So the first neighbor thinks 0, the second neighbor thinks 0, and the third neighbor thinks 1. So by majority, I'll say that this value is 0. And you can prove that this actually works if the number of errors is below the delta over 2.
So the errors are only in the aggregation on top, or also the code word on the bottom already?
After you finish doing the majority, you need to apply the decoder of your original code.
No, I understand.
The errors, this is all the input to your algorithm, right? So the errors can happen in both locations. The adversary can give you whatever they want.
So it starts by the adversary putting the values in V0?
No. The adversary can give whatever they want.
Okay.
It's adversarial, right? The point is that the adversary is guaranteeing you that there is a valid code word that's within distance, little less than delta over 2. And this is the promise, and you need to decode.
So I'm sorry, the adversary gives you both on top and on bottom?
No, just on top.
Just on top? I see.
No, he starts from a kosher word, and then he can modify it any way he
Oh,
wants.
so that's what I was asking.
But the kosher word
Words are on top.
did start from the bottom, but you don't know it. You don't get that as input.
No, you don't get it, but
Yes,
he starts with the bottom, he gives you what should be on top with error.
right.
Right, okay.
Yeah, exactly. Something else? No. Okay. All right. So, what if I had more errors than half, say? Then it could be very likely that every point here, the majority is not defined. It's going to see half zeros and half ones, and I won't be able to do this. So I can not go beyond that in this method. Okay, wait. Okay, so this is just what we said. Sorry. So in this method, we can never go beyond 1/2. But now I want to say that if this whole construction, we didn't know it, but there really is also a V2, then we can get an algorithm for going beyond 1/2. So I just want to stress that it's the same construction, exactly the same as before. It's just that for the algorithm for decoding, I'm going to now use V2. Okay, so this is kind of the new result, is that if your construction is part of a double sampler, then there is a least decoding algorithm that recovers from amount of errors going to 1. So for example, from 99% errors. Okay, so let's see that. Okay. Ken.
Before I go to V2, if I ignore V2 and I just look at this bipartite thing, should I think of this exactly as expander code of bipartite expander, or
Yeah.
like what?
Yeah.
And optimizing the parameters through the sampler or through the expansion would not give me slightly better things?
I don't know. I don't know. Yeah, I'm not an expert on these things, so I don't know. Okay, so let's look at this picture. Okay, so what did I mean by this picture? So here we have the first two layers of the sampler, and our code, we started with some code on n bits, and then we defined a new code over here that is over slightly larger alphabet. And now I want to try to describe an algorithm that gets something here that is guaranteed to be slightly close to a code word. What does it mean, slightly close? This yellow cloud, 1% of these guys are correct. 99% are junk. Okay? And now I want to find the code word that agrees with this 1%. This is my goal. Okay, so
You know in which area you have correct values?
no. If we knew which area, then it would be very easy. That's a good question. So the whole point is that you don't know, right? So, yeah. Okay, so how do we do it? So, okay, so now we go to the upper layer, and we see that this guy T looks down at its neighbors on V1, and this part is a sampler. So if there's 1% of good guys, also for this T, 1% of its neighbors are good guys. Okay, so T needs to find a local view for itself. So T, if you look 2 layers down, it's a subset of some number of vertices. Maybe the picture doesn't show it, but the cardinality of T itself is a constant with respect to n, right? Because you have, say, D neighbors here, and each one has D neighbors here, so it's still a constant. So T needs to basically find a local view just on the vertices down here that agrees with at least 1% of its neighbors. Okay, and since everything is constant, teachers can just, do exhaustive search over all possible local views until it finds some local view that agrees with epsilon fraction of its neighbors. Okay, there might be more than one, so because, you can have one local view agrees with this 1%, another local view agrees with this 1%. Thanks. Okay, so
What's going on
downstairs. So now,
A certain window now.
yeah, so now again, remember, instead of thinking of these only as bipartite graphs, I also think of them as set systems. So every vertex here, I think of it as the subset that it is connected to. And every vertex here is also the subset of the vertices down here that it's connected to. Okay, so the local view, you imagine that, you know, there was some W that all of these are consistent with. So T wants to, you know, find kind of the local view that it sees of this W and have it match this 1%. Of course, T doesn't know which 1%, so it generates a list of all plausible candidates. What is all plausible candidates? It's all values for the elements of T that are consistent with at least 1%. Okay, so this can be done in constant time for every vertex, so we do it for every vertex. This is the first step of the algorithm. What did we gain? What did we lose? On one hand, because of the sampler property, the W that we started with, the yellow cloud, is almost always present in the list. Because if this T was a good sampled well, W will be in the list. Only the T's that actually are in the error of the sampler might not have W. So that's good. We moved from only 1% W was present to 99% W is present. However, we now have a list. So previously, for every location, we had just one symbol, and now we have a list. So that's the negative. Okay. Okay, so now we have a list for every T. It's actually not hard to match the list of T1 to the list of T2. Because if these guys intersect, suppose T1 had just 2 candidates in its list. And T2 also had 2 candidates, and one of them was W. So the candidate corresponding to W here perfectly agrees with the candidate corresponding to W here. It could be that the other candidate is trying to confuse you and is colliding with W on the intersection. So this will cause problem. But if they don't collide, then you know that this candidate matches only one candidate here, and the second candidate matches only one candidate here, and you get a perfect matching between the candidates here and the candidates there. As I said, there could be collisions, and so you don't always get a perfect matching, but you can prove that with high probability, you do get a matching. Okay, so now we have for every T a list, and for every pair that intersect, you have a matching. Over the pairs T1 and T2 that intersect. So really there's an underlying graph here.
Sampling the T's that you're looking at.
Yeah, so let me talk about how we sample the T's. So really there's an underlying graph here. The vertices of the graph are the pairs, are the T's, and the edges are the pairs T1 and T2 that have some intersection. For example, their intersection has size, whatever the size of T divided by 3. I chose some constant. Okay, so you have this graph. And this graph, now if you think of the high-dimensional expander, who are these T's? These were the D faces in your expander. And what is this graph? It's really some kind of a random walk on the T faces. It goes from T face to T face by first choosing a T over 3 face and then choosing another T face, something like that. So we know exactly, almost exactly the spectral gap of this graph, and it's an expander, which is nice. Okay. So now we match the lists locally, and we want to find the global W. Remember now that W, for all the edges in this graph, we generate this matching. Okay. And now we know that on every edge, almost every edge, we have a matching, and we know that W, if it was present in T1 and in T2, it respects this matching. It's matched to itself. So we know that there is a choice of element in every list so that all of these matchings are satisfied. Not all, but almost all. So now how do we find this global W? You can try to start with T1. You will go over all possibilities. So let's suppose we started even with the good one and try to propagate and so on. But because some 1% of the edges are problematic, after 100 steps, you'll do an error. So it's kind of local greedy propagation is not going to work, as far as I know. But maybe it's already obvious that what you have here is something that we know. You can either think of this graph, and then these lists really give you a lift of the graph. Every edge, every vertex is replaced by the candidate, and every edge is now replaced by a matching. So what we have here is a lift of this graph. it's not a perfect lift because some edges are bad, so it's an almost lift. Or to some of us, this is just a unique gains instance. For every edge, you have this matching, which is a unique gains constraint. And you have this property, this promise that W is a solution to this unique gains instance. It satisfies 99% of the things. So all we need to do is find this W. Okay, but unique gains is conjectured to be hard, but not on an expander. So we know how to solve unique gains in polynomial time on a graph that is an expander. We run this algorithm and we get, okay, so this is the algorithm. Okay, so no, I think I'm out of time. So, yeah. So, okay, so this is the algorithm. For every T, we generate local views. For every pair, we construct the matching. We construct this global graph with unique constraints, and we run the unique gains algorithm. Okay, so let's end. So what have we seen? We've seen a transformation from a code C that was decodable from 1% of errors to a code C prime that is now least decodable from 99% of errors. So that's nice, but it's not I don't know, it's not very exciting for coding theorists because we already know of of least decodable codes that have much better parameters. So I think it's more interesting just as showing how these overlapping properties in the double sampler give you some power. The reason this is not optimal is because the rate of C prime depends on how many vertices I have in my double sampler. And for the current constructions that I know, this is not close to being optimal. Of course, if we get better double samplers, we might get something that's competitive. Okay, so let me summarize. Okay, so we saw this spectral local definition of high-dimensional expanders, and I tried to say that it's a pseudo-dense object. It's sparse, but it looks like it's dense. And we already had some examples where you could use this thing instead of the complete complex. And I showed you another such example. And probably there are other instances where you have some construction that is a tensorization or a power of your original instance, and you lose something because you did this power and your instance grew a lot, and maybe you could do a de-randomized power with this expander, so maybe. And the question that this raises is if you fix D, the dimension, and gamma, the bound on the spectrum, I want a gamma high-dimensional expander that's most efficient, that has the fewest number of faces. So now instead of trying to get it to be Ramanujan, we're optimizing something else. So I'm sure that algebra can be very, very important for this, but I don't know. I have no idea how to do it. And in general, I'm just interested in finding other constructions of double samplers, maybe random ones. It's interesting to point out that this is a broader object in the sense it doesn't have to come from simplicial complexes. So here we're talking about simplicial complexes, but here, for example, in the Grassmann example, it's not a simplicial complex. So maybe better things can be done. Yeah, okay, so that's it.